Hey gang, this is obviously the video for section 3.1. So you're gonna need this handout, obviously, but you're also going to need this handout called 3.1 Discovery. So this video will sort of address both of these. Might be some going back and forth, at least a little bit, between this 3.1 Discovery handout and the actual 3.1 Notes handout. So make sure you have both of those out in front of you. Also, a protractor and maybe even a ruler. You can probably get away with just having a protractor because protractors have, on the straight edge, have the ability to measure inches, and that's really all we care about. So make sure you have a protractor as well as these handouts. So here we go. This is obviously the start of a whole new unit. We're going to do one more unit on trigonometry. Still a little bit more to cover with all that stuff. So this will be our third and final unit on trigonometry. Let's get started. Recall that if we are asked to find missing measurements in a triangle, we have certain methods that we can use as long as the triangle is a what kind of triangle? That's right, a right triangle. So we definitely have a lot of experience figuring out a unknown angle or an unknown side as long as the triangle is a right triangle. I'll just kind of not randomly, but skip back to section 1.3. This is a part of the 1.3. You don't need the paper out, but you might recall examples like this where you were trying to find this missing side, and you had, SOHCAHTOA definitions. You could make like an equation using SOHCAHTOA to find this missing side. Same with an example like this. When even if you had to find an angle, you could use like a SOHCAHTOA equation and do like an inverse tangent or an inverse sine or whatever applied there. Or you could just use the Pythagorean theorem. If you knew 2 out of the 3 sides and needed to find the third side, Pythagorean theorem, right? So that's sort of what I mean from this first little recall statement, that in the past we could easily find missing measurements, but as long as the triangle was a right triangle. So, what that kind of leads into here is that we're going to now be solving triangles that are not right triangles. And those are called technically oblique triangles. You don't need to remember that term. It's not a very big vocabulary word for us. Again, the biggest point on that is that that's what we're going to be doing in section 3.1, and then again in section 3.2, is solving all missing measurements of a triangle that does not happen to be a right triangle. So, how are we going to do that? Well, that's where the law of sines comes into play. So the title of section 3.1 obviously is the law of sines. And the law of sines might be a little weird at first, but hopefully you get the hang of it pretty quickly, because the law of sines is just a formula. So consider this picture right here, just some random triangle, and it's labeled like so. We have all the angles labeled A, B, C. So angle A, angle B, angle C, and you'll probably notice that we're using capital letters and then the sides are also labeled A, B, C. But again, notice that the sides are labeled using lowercase letters, whereas again, the angles are uppercase letters. Also notice that side A is directly across from angle A. It's no coincidence that side A is right here and angle A is right here. Same with side B being across from angle B and side C being across from angle C. So if your triangle is labeled like so, then here's what the law of sines formula is. It says side A over the sine of angle A is going to be equal to side B over sine of angle B, which is also going to equal side C over the sine of angle C. So as you're finishing writing that down, you'll probably notice that this is a weird formula because there are two equal signs. That's kind of weird. Well, you're going to see that, pretty quickly in the next example, the first example, that we're only going to be using two of these fractions at a time. We're never going to use the entire law of sines formula, to find one thing. We're just going to be using like those two fractions equal to each other, or these two fractions equal to each other, or the A fraction equal to the C fraction to solve for whatever we need to solve for. Let's see what I'm talking about here. So example 1 says, solve triangle ABC if angle A is 64 degrees, angle C is 82 degrees, and side C is 14 centimeters. All right, really quick comment. This SAA triangle, not going to address that yet. So just forget about this little note or comment right here. Just forget about that for now. The other comment I want to make really quick is that, yes, these measurements would apply, ABC and stuff, to a picture like this. But you're going to discover pretty quick here as we go through examples that it's not going to help you very much, or at least I don't think it does, to actually draw the picture. Having the picture drawn and, angle A labeled with 64 degrees and side C labeled, like I don't think, like normally it does, right? There's been dozens and dozens of situations in your math lives where drawing the picture like really helped a lot. I guess this is just not one of those times. So it's like one of the exceptions, I guess. So we don't need to draw the picture, bottom line. All we really are going to care about is what we are given and how we can use this formula to solve for something that we don't know. And we have to solve for everything else. That's what it means to solve the entire triangle. So it looks like we need to figure out angle B and then side A and side B before this is all said and done. Okay? So considering what they gave us, think to yourself for a few seconds, what could we find next? Whether it's using like 2 out of these 3 fractions set equal to each other, or maybe something else that you learned in, I don't know, middle school geometry class or some middle school math class. What could we find next? Well, sorry to interrupt anyone that might be speaking out in class or raising their hand or whatever, but if you thought, hey, we could use the law of sines formula to get little a, like we could use the c's fraction and the a's fraction because we know like 3 out of those 4 variables. So if you said that, like, okay, like notice this box up here really quick. But if you said like, hey, we can find little a, you are absolutely correct. But you know what? I wonder if anyone thought that, hey, wait a minute. If we know 2 out of the 3 angles, don't all the angles of a triangle always add up to a certain number of degrees? What is that? Do you remember from like maybe middle school math? All the angles of a triangle will always add up to what? 180 degrees. So in this particular example, we could actually do that first, and that's what I would probably recommend doing first, as long as you can, you know. Angle A is 64, angle C is 82. So all you got to do is subtract those from 180 to get what angle B must equal. Again, so please remember this, going from here on out. All the angles of a triangle will add up to 180, whether it's a right triangle or not. So angle B is 34 degrees. Now we're going to move on to figuring out side A. So again, I know this is like the very first example, so we're still getting our feet wet, still trying to get the hang of like what the heck is going on here. But you know, I hope you're starting to realize, or I hope you understand why this would get us somewhere. You know, like we have, so it's like we have big A, so we're going to plug in for big A. We know little c, so we're going to plug in for little c. And we know big C, so we're going to plug in for big C. Then we'll only have like one actual variable that we can then solve for. So there you go. So once we plug in what we know, we'll be able to solve for what we don't know. Because there's only one thing left over in this equation that we don't know, and we can solve for it. So how do we go about solving now? What would be like maybe the very next step, solving for little a? Think about it for like a few seconds at least before I spoil it. What would be the next thing to do, solving for little a, you know? Maybe what you notice is that this is what, you know, we call in math, you know, a proportion. And when you have a proportion, you can do something called cross multiplying. So if we multiply little a by the sine of 82, hey, notice that I actually didn't calculate what the sine of 82 is. You know, maybe that's what you thought the very next step was. And it's not like you're super wrong about that. Like I can't really say you're wrong at all, but let's write it down like this. So a times the sine of 82 equals, and then this other cross multiplying, 14 times the sine of 64. All right? Now, really quick comment that's going to be a reoccurring theme. Don't actually go to your calculator and to try to figure out the sine of 82, because you're going to end up like approximating that. You're going to end up rounding it off. And I would highly recommend, just because it's like, you're like just in the interest of coming up with the very bestest answer, most accurate answers you can, let's try to avoid doing any rounding until the way end, right? Because then, like, if you round this and then you round this and then if you're like doing operations with rounded, your final answer might be like a little bit off of what it could have been, you know. So in the interest of being as accurate as possible for like our final answers, let's avoid rounding. So like leave it like this. And then the last thing we got to do in order to solve for little a is what? Divide both sides by the sine of 82. Okay? So now let's go to our calculator. Make sure your calculator is in what mode? It's got to be in degree mode if we're going to be doing like 64 degrees and 82 degrees. So make sure your calculator is in degree mode, and then you're just going to do 14 times the sine of 64, and then all divided by the sine of 82. And if we're rounding or truncating to 3 decimal places, this is an acceptable answer. I don't know what the truncated answer would have been, but I'm pretty sure I would have rounded here. About 12.707 centimeters. So that's little a. And then the next move, the final thing we got to solve for is what? What do we still have to figure out? We still have to figure out little b, side b. And we're going to do that by using another law of sines, proportion, okay? And again, another like little nuanced detail here. We're definitely going to have like the b's fraction, but are we going to set it equal to the a fraction or the c fraction? What do you think would be quote-unquote better? Well, I hope you're thinking the c fraction, because that way we're not using an approximated side a. Like if we want to come up with like the very best answer for side b, if possible, we want to avoid using, an approximated answer from another measurement. So this is exactly 82 degrees, exactly 14 centimeters. Exactly 34 degrees for big B. So I'm going to use these two fractions on purpose, just if nothing else, just to get like the very best answer possible for side B. All right? It's not like it's the end of the world if you set the B fraction equal to the A fraction, but hopefully point taken there. And then hey, nothing new, it's just same thing again from before. We're going to be cross multiplying on our, in our quest to solve for little b here. So cross multiplying, again, wait until, one more step until we start going to our calculator. So b times the sine of 82 equals 14 times the sine of 34. Then, same as before, we're going to divide by that to get little b all by itself. Then we go to your calculator and type that in really quick. Just to, make sure that we know how to push these buttons. I have no doubt that it's going to be no problem. But 14 times the sine of 34 divided by the sine of 82. Make sure you're able to get 7.906 centimeters for your final answer. Okay. So that's the first example. Pause if you need to finish writing things down or whatever. But the second example, okay, again, just ignore this for now. I'll follow up on this a little bit later. The fact that this is an ASA triangle, what the heck does that mean? Don't worry about it for right now. The second example is fairly similar to the first example. I guess the biggest difference is that here's what they give us. Big A, big C, and little b, right? Would we be able to use a law of sines proportion right now with what they gave us? Because we still need to figure out big B, little a, and little c. Could we theoretically use a law of sines proportion as our very first step? The answer is no. Because wouldn't we need to have like both A's and then something else? both C's and then also at least one other thing, and then both B's? So no, like, and that's the difference. So here, it's a good thing that we have both angles because we can just subtract them both from 180 to get this ball rolling. And so that's going to be the very first move, and there's nothing else we could have done to start this off. So it's a good thing we know from middle school that, I mean, I hope they taught you this in middle school, that all the angles of a triangle, no matter whether it's acute or obtuse or a right triangle or equilateral or scalene or isosceles or whatever. I know you're impressed I remembered all those, like, off the top of my head, but it doesn't matter. All the angles will always add up to 180 degrees. So there's my angle B. Now we have, now we have both B's. So now we can use the B fraction and then whatever else we want, Looks like I'm just picking the A's, But now that I have both B's, I can figure out, either little a or little c. So I'm going to make that proportion, plug in what we know, because we can now solve for side A. Once again, nothing new here to reveal, to teach you. Once we have the proportion set up, we can cross multiply and do everything we did in the first example, just all over again. So yep, the next thing we're going to be doing is dividing both sides by the sine of 117.5. And then that'll get A by itself over here. And then go to your calculator for those calculations. And it turns out that little a is going to be about 8.696. All right? And then, I mean, I hope at this point, it's only the second example, I hope you're sort of catching on by now, at least to a certain extent. So what's the next thing we got to do? What's the only other thing left to solve for, right? Isn't it little c? And so let's set up a law of sines proportion. And again, notice how I'm picking the b fraction again, as well, along with the c's fraction to go after little c. Again, it's not the end of the world, but let's try to get the very bestest answers we can. So check it out. There it is, throwing everything in there, obviously except for little c, which we're trying to actually solve for. And then again, same old, cross multiply, right? That's what we do when we, again, I hope I'm not going too fast, but hopefully you're picking up on all these moves now. Cross multiply is the next step, right? After we set up the proportion. And so 12 times the sine of 22.5 equals c times the sine of 117.5. And then what's the next step as we look to, just solve for c? I'll give you at least a couple seconds here. Like, what's the next step to solve for c? That's right. Divide by the sine of 117.5. So on your calculator, you're going to be doing those calculations, and you should be getting about 5.177. Okay? Now, at this point in time, I believe this is where I'm going to kind of have you switch over to this 3.1 discovery. In a minute or two here, well, maybe more than a couple minutes, but you're going to actually pause this video, do like a hard pause, and see if you can kind of like run through these 3 problems. Okay? There's a number 3 on the back. So, but let me kind of get you started before you do that hard pause on the video. So this handout, here we go. You're going to need a protractor. If you also have a ruler, I mean, I don't think you're going to need a ruler because the protractor will take care of everything. But let me get you started with what we're doing here, okay? All you're really doing, okay, like in general, is we're going to try to draw, like so, again, if we're considering a triangle labeled like so, we're going to literally try to draw that triangle that have the following exact measurements. Big A is 50 degrees. Little a, side A needs to be 5 inches. And then side C needs to be 4 inches. So there might be a handful of you that might not need any help to get this started, but usually people need help. So let me try to help you figure out like how you're at least going to get this started, and then like I want you or the substitute teacher, whatever the case might be, do like a hard pause for a little while. So here we go. So basically, you're going to take your protractor or ruler and you're going to draw side C first. So side C is locked in at 4 inches. So you're going to draw that purple side of the triangle first, side C, so measure out 4 inches, and you're going to draw that, okay? Then you're going to take your protractor, and this is how you use a protractor, okay? We're going to draw angle A next. And again, angle A has to be locked in at 50 degrees. So what you do is you put the whole of the protractor like right here on the very left end point of side C, okay? And then you notice like, well, you don't notice, but then you look for 50 degrees, okay? Because we want to make angle A exactly 50 degrees. So you put like a mark on your paper like right there at 50 degrees, okay? Then you would draw this pink side, and I believe this would be side B, eventually. Now we don't know how long side B needs to be. So just draw this line, this side, like, fairly long, because we don't actually know how long this side is going to end up being, right? So that's what you do. And then the other measurement that's locked in is little a equaling 5 inches. All right? So that, remember, side A is going to be over here. So this is where side A is going to be, right? But we don't know what angle it's going to be at. We just know that side A needs to be 5 inches. So you take your protractor or your ruler and you position it right here, and you twist it and you position it until you're pretty sure that you found like the proper angles, right? Where this side A, like see the 5 inches, would have to be exactly 5 inches, okay? And that's pretty much what you do, right? And I believe it's like the same don't want to spoil that too much. So at this point, in a second, you're going to do a hard pause, and then you're going to unpause it whenever, this has sort of run its course and people have think they've accomplished or run through number 1, the rest of it, number 1, number 2, and number 3, or people just got really, really stuck. I hope it's not the latter. I hope you're going to unpause this after you've sort of run its course here. But remember, all you're really trying to figure out is the length of side B, really. But all right, do a hard pause now, and then unpause it when you are ready. Okay, I'm going to now carry on as if you've unpaused, and everyone has already given this a pretty good go. So here we go. Number 1 should have turned out sort of like this, right? And I think the length of side B, so the length of side B, what you should have got was basically 6.5 inches. So hopefully you figured out that the length of side B here was like 6.5, okay? Looking kind of like this. Now number 2, I hope number 2 didn't throw you too far off, because I mean, here's what eventually happens. You have a side A of 3 inches, okay? And again, I hope this didn't like break anyone's brain, but here's what actually happened. A side A of 3 inches, 3 inches, like you were trying to have it connect with side B over there, and it just wouldn't touch. So here's what maybe a few of you realized. It's impossible to draw a triangle with those 3 measurements. There is no triangle to be drawn in number 2. All right? So sorry if that was like a little bit of an unfair request. But again, I hope you at least in that, getting stuck, like realize something and discovered that in some kind of minor way at least. But yeah, it just won't link up. It just won't. And then check out this, what happened in number 3, okay? So maybe when you tried to link up this side A of 3 inches, maybe you got a triangle like this. But, hey, maybe you noticed, check this out. Oh, I want, oh, come on, man. No. Just want that to be... Just wanted it royal blue, that's all. So look, maybe your 3-inch side A got to here, but I wonder if anyone noticed that you could have also connected 3 inches right there. So the 3-inch line for side A could have touched over there in 2 different spots. So check it out. What that means is you actually could have drawn 2 different triangles based on these original 3 measurements. So if you got a side B, which again, remember side B is over here. If your side B was basically 3 inches also, then you were pretty spot on, like just over 3 inches. Or if your side B was like just over 2, like about 2.2 inches, then that was also correct. All right. Anyway, here's how that builds back into like the notes. Okay. So here's what we're about to move on with when it comes to like just like these example problems. Okay. The first couple examples, right, had this little thing written here that said like SAA triangle or ASA triangle. I'll try to make this a quick, aside here, but maybe you remember from geometry class, you know. I mean, you should have, I know there's a few exceptions, but you should have taken geometry before pre-calculus, you know. And if you did, maybe you remember how in geometry you had this like SAA sort of like postulate or something, or maybe it was written as like AAS, you know, angle, angle, side, or side, angle, angle. Same thing. And how that was used was like, if you could show that one triangle's angle, angle, side was the same as another triangle's angle, angle, side, you could go ahead and say that that both triangles were 100% congruent to each other. You didn't need to show that all the measurements, like all the angles and all the sides, were congruent, as long as you could only show, you know, in order, angle, angle, side, or side, angle, angle, you know, or one triangle's angle, side, angle in a row was congruent to another triangle's angle, side, angle in a row. That was enough to kind of say like, oh, these two triangles are the same in every way. So anyway, what that really means for us is that in a situation like this, there was only one triangle. There was one way to kind of solve for everything else, right? There was only one triangle that could have resulted from these three, you know? Same with this, like 40 degrees, 22.5 degrees, and 12 inches. There was only one triangle that was going to ever result from these three measurements that were like locked in stone. Well, now what we're about to do is see what happens when what you have is technically side-side angle, which, if you recall from geometry, if you even had geometry already, this was not one of those postulates, you know, that would have resulted in, you know, one and only one possible triangle. Okay? So let's see what happens when we have, you know, what's basically called the ambiguous case. All right? So here's what we have. We have big A, and little b. Right? So what can we find first? Don't think too much about like, oh, is this like side angle or angle side angle? Just think about like what we have, what we were given, and what that allows us to solve for. Okay, think about that for a couple seconds. What could we possibly solve for next? Well, hopefully you've realized that, oh my gosh, we only have one angle. So we can't find like one of the other angles just because of how they add up to 180. Okay, we only have one angle. So what else? It's like maybe you notice that we have both A's and one of the B's. So what that's going to allow us to do is set up this proportion, the A's and the B's, from the law of sines. Okay? Now, before we move on with this, here's what I really want to point out. Here's what I really want to emphasize. Way more than like, oh, is this angle side angle? Is this? Don't even worry about that. What you're going to worry about, what you're going to notice, what I want to highlight is that what we're solving for now is an angle. Okay? That's going to be, you know, where the rubber meets the road here. You know what I mean? Again, it's not, you don't have to notice, you don't have to draw the picture, you don't have to notice whether it's, you know, angle side or side angle, okay? Just pick up on the fact that what we're now solving for is an angle. We're solving for big B. Well, in order to solve for big B, we first are going to have to get the sine of b by itself. So, okay, cross multiply, and then what? Again, we're not going to be able to figure out big B until we get the sine of b by itself. So then we're going to divide both sides by 33, and we're going to get to here. Okay? So what do we do next? What do we do next in order to figure out what angle B is? Maybe you remember from the past couple of units or whatever, this is where what we could do is bust out an inverse sine. This should seem at least a little familiar. So to get side B, we're going to do an inverse sine of all of that. All right? And so make sure on your calculator you're able to get that. Okay? Inverse sine of all of that fraction, and angle B is about 41.359 degrees. Okay? But this is where we get to like a major plot twist. All right? For comparison, what if I asked you to solve, like, I don't know, the sine of x equals root 3 over 2, just as an example. Like, remember doing this? Sine of what? The sine of x equals root 3 over 2. Don't you remember how there isn't just one answer possible? That there's actually an infinite number of solutions, you know? So here, like back up here, look. The sine of what angle equals whatever the heck this is. There's actually an infinite number of answers, right? But I mean, what we're doing here is like an actual angle of a triangle, of like an actual triangle, right? Hopefully. So it's not like there's going to be, you know, everything coterminal to 41.359 degrees. But guess what? You know, we need, again, here, so getting back on track here with like the major plot twist, we at least need to check the quadrant 2 answer. This you can think of as the quadrant 1 answer, but there's also, considering that it was like the sine of b equaling something positive, this turns out to be positive. So the sine of something, of an angle equaling something positive, you're talking about quadrant 1 or quadrant 2. So this is the quadrant 1 answer. How would I figure out what the quadrant 2 answer would be? Well, it's that. How do we get that? Where did that come from? I wonder if anyone can realize this on their own, okay? How did I get this as like the quadrant 2 answer? Well, all I really did was subtract 41.359 from 180 degrees. So I don't know if you want to write that down, like 180 minus 41.359, because, and look, it's not because of this, right? It is not because of this same reason. It's because of this reason, okay? Sorry, I know I'm going a little bit off the screen here. Maybe a little too much. So let me, well, I don't know. Well, anyway. So if this angle in quadrant 1 is 41.359 degrees, then the angle, like over here, the reference angle. So here's the quadrant 2 answer. Its reference angle also needs to be 41.359 degrees. So this is 41.359 degrees. This is 41.359 degrees. So that's why, because then, all the way to 180 minus this would be what your quadrant 2 angle is. So we can follow up more on that later, but all you really do. Now, here's what you have to do next. What you have to do next is figure out, well, okay, is there really two answers though? Like, would 138.641 degrees, does that actually make sense? Could that be my angle B? Right? This could be my angle B, but could that be my angle B instead? And so here's something worth pointing out right now. It's not like it's one or the other. It's not like, oh, which one is correct? Here's what it really is. It's like, okay, this could be my angle B in one triangle. Could this be my angle B in a second possible, entirely different triangle I can draw? So, but here's the thing. 138.641, if this is your angle A, like this is locked in. Angle A is locked in stone. This angle B is too big. It's too big. If that's your angle A, this cannot be your angle B. Otherwise, you've already gone over like the 180 degree limit. So we had to check this, but it turns out that there's only one solution here, and so our angle B is only that. And now we can move on with like solving the rest of it. And now that we know angle B, we could get angle C. And then now that we know angle C, we can do the same old tricks to get little c. So copy that down. I'll give you like another 15 to 20 seconds. Hopefully you don't need to do a hard pause. But hey, if you need to do a hard pause, that's totally fine. But I'm going to move on to the next example now. And here we go. So same old ambiguous case, big A, and little b. Again, I'll try to keep reiterating this. Don't spend any energy trying to figure out, well, is this angle side? Is this side angle? Don't even worry about that. Just worry about what you have, and if you have enough of the law of sines, if you have both angles. See, here we don't have both angles. But we can go after big B, because we have both A's and one of the B's. So again, the bottom line here is we can set up a law of sines proportion and try to solve for big B, But the same sort of situation is going to play out here. We cross multiply to get to here. Okay, 10 times the sine of b equals 20 times the sine of 50. We get the sine of b by itself by dividing both sides by 10. Okay. Now, again, how do we figure out, angle B from an equation like this? What's the next thing to do, right? Oh, I hope the same thing as the last example. We're going to take the inverse sine of all of that, whatever this is, but let's try to leave it like this, so we don't have to round anything. inverse sine of all of that. Take like 20 to 30 seconds here. What do you get? Like, get your calculator out. Do the inverse sine of that. Another like 10 seconds. All right. I hope there's not too much of a uproar going on, because it turns out that you get some kind of domain error or something like that. When that happens, there is no solution. It's like number 2 back here, where it just it just literally couldn't connect to make a triangle. So that's what happened here. No solution. If you would have gotten something, you would have had to again consider a second possible angle, from quadrant 2. But you could also get, look, no solution. No solution is possible, because that's what happened here. All right. Now the last example. Ready? One more situation. Maybe you can guess what's going to happen here based on everything we've done already today. So here we go. Once again, big A, and little b. We don't have enough just to, again, if we would have had 2 out of the 3 angles already, we could have just found the third angle. But again, this is our only recourse right now. The A fraction equal to the B fraction. And again, we are destined to end up doing an inverse sine. That's in our future, for sure. An inverse sine is in our future, which means we have to consider, stop that. Which means we're going to have to consider 2 answers. And I wonder what's going to happen with that. So, same old stuff. We cross multiply. 12 times the sine of b equals 16 times the sine of 35. Divide both sides by 12 to get the sine of b all by itself. Now what do? Right? We do an inverse sine to figure out what the angle is. Okay? Inverse sine of all of that. And so, what your calculator is telling you is about 49.886 degrees, right? But remember, this is the major plot twist that you got to try to learn, as soon as possible. There is also a quadrant 2 answer that angle B could equal, and all we got to do is subtract that from 180, and here is your other possible angle B. All right? But here's the thing. In this problem, angle A being 35 degrees, obviously angle B could be this, but you know what? This would also work for angle B. If that's our angle A and that's our angle B, there's still degrees left over for angle C. Okay? So here's what we have. We have 2 totally different solutions. We have one solution where we choose this as our angle B, and then we're going to have an entirely different solution where we choose this as our angle B. It's like a fork in the road, and if we go down this path, we get, certain answers, but instead, if we go down this path, we get different answers. So here we go. solution number 1 is where we choose this as our angle B. Okay? And if that is our, remember, these are locked in stone, you know? So if this is our angle B, then that is going to be our angle C by doing, 180 minus 35 minus 49.886, And then what else do we have to find? We got to find little c, And I know, big hypocrite, but we don't really have a whole lot of choice here. Like we kind of need to use an approximated answer to get little c. Oh well, again. But so again, it's this angle B that leads to this angle C, which is going to lead to this little c. So that is one set of answers for solution number 1. But what we're about to do is now pursue solution number 2, where instead of this being our angle B, we choose this as our angle B instead. So here's solution 2, where angle B was this. It's like the Marvel multiverse, different universes where we had like a different angle B. So if this was our angle B instead, that would lead to this being our angle C. Remember, you're still using these original measurements. But now this is our angle B, which leads to this angle C, which is going to lead to this as our side C. So like B2, C2, big C2, and little c2. So 2 entirely sets of solutions based on like how there was actually 2 different triangles that could have been drawn from the original 3 measurements. Okay? And that about does it. So what you're going to do now is try your 3.1 homework. Okay?